Okay, Algebra 2 students, this lesson is on 5.2. It's talking about graphing these rational expressions. So they look a little bit different. So we're going to talk a little bit about parabolas that you know how parabolas work. We've done them before. And then you're going to be able to do some similar translations with a rational expression. They work very similarly to the quadratics. So let's just very briefly review quadratics. This y equals x squared is the parent quadratic, okay? And this here, I'm going to turn this one on, y equals x squared plus 4. This 4 right here pushes the parabola up 4 units, so it translates it up. So now the vertex is here. So do you remember the HK or the vertex with vertex form of parabolas? It's the same idea. I'm going to turn this one off and this one on. This one, x minus 3, that shifts the parabola to the right 3. Okay, remember that this parabola is sitting here on the x-axis, and what makes y 0? 3 makes y 0. So that's why it seems a little bit like in the opposite direction that it's going. Okay, so it shifted it to the right. The last one is shifted down 2. That's what this one is doing. See, it's shifted down 2, and it's shifting to the left because of this plus 3 right here. 3. And so the vertex was changed. So if you remember, the vertex was HK. So the vertex is -2, -3 for this parabola. So it's the same concepts that we're going to be using for rational expressions that we have for parabolas. So right here, this right here is your parent function of a rational equation, okay? Y equals 1 over x. And you'll notice it has these 2 branches. And if you zoom out, you'll see these branches are stuck in the first and third quadrants, okay? And the reason that's happening is if you stop and think about it just for a minute, we cannot divide by 0, correct? So if you cannot divide by 0, x can never be 0. So our domain is limited. It's all real numbers except 0. X's cannot be 0. So what happens here is you end up with something called an asymptote. So we have a line here at x equals 0, a vertical line, and what happens with the graph is as x gets really small and close to 0, we get closer and closer to this line, but we don't touch it. Okay? Same thing down here. As x approaches 0 from the left, we get very, very close, but it never touches it. Okay? So these are called asymptotes. They're like limits. And this is the parent function. So what do you think might happen if, I'm going to leave those 2 up, we add 2 to it? So you'll notice when we add 2, we pushed the graph up 2. Okay, so my vertical asymptote stayed the same. Oh, let me go back to this, sorry. Talk about horizontal asymptote. So the horizontal asymptote right here, you'll notice, is y equals 0. So this graph is approaching that line, but never going to touch it. And this graph, as x gets really small this way, it's approaching this line, but it's never going to touch it. So what happens when we add 2, just like with the parabola, we shift the entire graph up 2. So you'll notice that the vertical asymptote is still x equals 0, but our horizontal asymptote is now at 2. Do you see that? The horizontal asymptote is happening right here. All right, right here. And adding 2 shifted that entire graph up. Just like the parabola, if I add 3 down here with my x, here I added 2 to the entire function, okay? Here I'm just adding 3 to x, okay? That shifted it to the left, okay? So my asymptote, my vertical asymptote is no longer x equals 0, like it is for the red function right here. It's shifted, and it's at x equals -3. So here is x equals -3 right here, where my mouse is rolling over it. And you'll notice there is an asymptote there. That graph is approaching it, but it's never going to touch it. Okay? The fourth one is like a combination of a shift left-right and a shift up-down. So the -2 shifted the graph down. So you'll notice that the horizontal asymptote is at is at -2. It's pushed it down. So here's the purple one. The horizontal asymptote is at -2. It also shifted the graph to the right 4. So you notice the vertical asymptote is now right here at x equals 4 instead of x equals 0 like it was for the parent function. So these things are operating just like the parabola with the HK vertex form that we had. So this is what it looks like. Remember we talked about the vertex form for parabolas. This is the form for a rational equation. So you'll notice if we have something like f of x equals 4 over x plus 2 minus 1, let's say. Okay, let's make it like this. We'll make it a little bit easier for the first one. Oops, sorry, undo. Here, I'm going to make this a little bit easier. We'll make it look exactly like this one up here. So we'll make it an x minus 3, x plus 2, like this. So what this graph would look like, very sketchy graph, my vertical asymptote, this graph is going to be shifted completely up too. So let's do the horizontal asymptote first. So the horizontal asymptote is going to be y equals k. So this is k right here. So y equals k is going to be my horizontal asymptote. So I'm going to make a dotted line. Your asymptotes usually are dotted lines right there at y equals 2. So this would be y equals 2 is the horizontal asymptote. And h, x equals h, so notice it's going to be x equals 3 is going to be my vertical asymptote. Okay? And that looks like this. I'll put it about right here. And that's at 3, and x equals 3 is my vertical asymptote. And then the branches of my parabola, or excuse me, my rational function, are going to be like this. It'll look something like this. And you're going to have your calculators to help you graph this. Okay? So we have a horizontal asymptote here at, and this is why they are there, here at 3, because x can't be 3. We can't divide by 0. So x can never be 3. Okay? And if x can never be 3, okay, this whole number this number right here, this number can never be 0. There's no way that 4 divided by x minus 3 can ever be 0 if this cannot be 3. It's impossible. So if this can't be 0, y, or f of x, can never be 2. And that's why there's a horizontal asymptote right there. Okay? So what you're going to be doing in some of your homework problems is working with this idea. Okay? So this first problem here, you're always going to want to factor first. Okay, so I'm going to factor this equation. So f of x equals 5 over x minus 3, x plus 3. So my vertical asymptotes are going to be at x equals 3 and x equals -3. Because x can never be 3. X can't be 3. You cannot divide by 0. X can never be -3. You cannot divide by 0. So you are going to have vertical asymptotes at x equals 3 and x equals -3. So let's actually look at the graph of that on Desmos. Okay. Okay. So here's the problem right here. This is the graph. This is what it looks like. So notice that we have a horizontal asymptote at x equals 3, which is right here, and x equals -3, and you've got a branch happening this way and a branch happening this way, and this funky looking thing in the middle. Okay, so so the asymptotes are going to help you sketch these graphs, and hopefully when you look at it in here, you notice if I have it factored, it's the same exact thing. Okay, it does have a y-intercept. Okay, look at this. if x is 0, I would plug a 0 in here, right? If I plug a 0 in for x squared, I'm going to get negative 5/9. So this point right here is, if you did that on your calculator, you'd see that that's negative 5/9. Okay, that is the y-intercept. And there is no x-intercept because we said there's an asymptote right there you can see at y equals 0. Because like we were talking about earlier, this denominator can never be 0. So if the denominator can never be 0, this whole fraction, 5 divided by something that's not 0, is always going to be something that isn't 0. So y is never going to be 0. So that's why there's an asymptote there. Okay, one more example. Here's another example. So you've got this equation here, and I'm going to factor the denominator here. X, 3, 2, that's a negative. That's a positive. So our domain is limited. X equals negative 2 and x equals 3. Those are where our vertical asymptotes are going to be. Our horizontal asymptote is going to be y equals 0. Because if this denominator can never be 0, the numerator is never going to be 0. Okay, it's 8. It's always going to be 8. So there's no way that y can be 0. Okay. If I wanted to figure out what the y-intercept was, okay, that's when x is 0. If I plug a 0 in here and a 0 in here, I'm going to get a negative 8/6, which is negative 4/3. So my y-intercept is this point right here, 0, negative 4/3. So when we go to graph it, turn this one off. This is what it looks like, very similar. And you'll notice that the vertical asymptotes are at x equals negative 2 and x equals 3. Okay. There's one more I'm just going to point out to you very quickly. This last one, this equation here, you'll notice it's not exactly in this format, is it? It doesn't really look like this. So graphing this is going to be a little bit different, but we can at least think about some things. If you look at this number here, x is going to be squared, right? So no matter what number we put in for x, we're going to square it, and it's always going to be positive. So if we add a positive number to 5, we are always, always, always going to have a positive number as the denominator. So we're not going to ever divide by 0. So we are going to have no vertical asymptote. Okay? We are not going to have a vertical asymptote. So let's just take a look at what that would look like. Okay? Sorry. That is this very last one I have graphed for you. Check out what that looks like. Isn't that cool? So what's happening is there is no vertical asymptote, but it looks like we might have an asymptote at y equals 0. The graph is approaching 0. Check that out. Even though it crosses 0 right there. So if when x is negative 2, no, I'm sorry, when x is negative 1, y is 0. So that point right there, okay, is negative 1, 0, and that is totally on the graph, okay? But what happens when x gets really, really big? So what's happening when x gets really, really, really big, the denominator is getting faster, getting bigger a lot faster than the numerator. So you'll notice as we get really big, keep looking, it looks like it's touching the x-axis, doesn't it? But it isn't. See? It's getting very close. It's at 0.022. So if we keep going and going this way, it looks like it's getting close to the x-axis, but it's not. It's just getting very, very close. So it is approaching as x gets really, really big. If we go to the negative direction, the same thing is happening. Look at that. Okay? So it's a pretty cool phenomenon. These graphs look pretty funky, and they do some really cool stuff. Luckily, you have computers and graphing calculators to help you graph these. And we're going to be talking about some cool aspects of these graphs throughout this entire chapter. So hopefully this video helps a little bit.